We conclude our study of functions by looking at some properties of functions. Now, recall that a function may send several variables or several elements of its domain to the same element of its codomain, as long as one element from its domain is not sent to more than one element of its codomain. Right? Each element from the domain is sent to a unique element in the codomain. What this means is an element of the codomain can have multiple elements from the domain being mapped to it. If a function has the added property that each element of the codomain has at most one element from the domain that is sent to it, then we say that this function is one-to-one, or that the function is injective, or that the function is an injection. So formally, let f be a function from a set x to a set y. We say f is one-to-one, or injective, or is an injection, if and only if, for all elements x1 and x2 in x, the following statement is true. If f of x1 equals f of x2, then x1 equals x2. Alternatively, we can also write this as if x1 does not equal x2, then f of x1 does not equal f of x2, right? This is the contrapositive. So either statement is correct. Right, so here's an example of a function that is one-to-one. Right, in the arrow diagram, you can see that each element in the codomain has only a single arrow to it. So here's an example of a function that's not one-to-one. Like this element has multiple arrows going to it. So let's look at these two functions right here. Are either one-to-one? Well, to be one-to-one, every element in the codomain has to have only a single arrow. Right, U has none, V has one, W has one, X has one, Y has one. So F is one-to-one. Now let's look at G. All right, so U has one, V has none, but W has two. We can stop looking. G is not one-to-one. All right, so that's for functions from a finite set to a finite set. Let's look at infinite sets. So we're going to have two functions here. F will be from the reals to the reals. G will be from the integers to the integers. And they're defined as follows. F of x is 4x minus 1. G of n is n squared. We wish to determine whether either of these two functions is one-to-one, and of course justify our answer. So that is, if it is one-to-one, prove it. If it's not, provide a counterexample. Well, if we look here, this appears to be one-to-one, right? There's only one x that will send 4x minus 1 to a specific value y. So, in fact, f does define a one-to-one function. All right, so we have to prove it. And the proof is pretty straightforward. This is an algebraic proof. So we say let x1 and x2 be real numbers such that f of x1 is equal to f of x2. The goal is to show then that x1 has to equal x2. So if this is the case, then 4x1 minus 1 has to equal 4x2 minus 1. If we add 1 to both sides, then 4x1 will equal 4x2. We can now divide both sides by 4, and we get x1 is equal to x2. That's what we wanted. So we can conclude that f is 1. Now, what about g? Well, we're dealing with integers to integers. Well, 2 squared is 4, and negative 2 squared is also 4. Right? So this actually is not 1-to-1. And I already gave the counterexample. Right, so counter. Let x1 be 2 and x2 be negative 2. Right, so it is obvious that x1 does not equal x2, which means that f of x1 cannot equal f of x2. F of x1 is going to be 2 squared, which equals 4, and f of x2 is equal to f of negative 2, which is, I don't want that negative 2 in there, sorry. Negative 2 squared, which is also 4. I actually should have been using g's, not f's. So g of x1 does not, I'm sorry, g of x1 does equal g of x2, which means that g is not 1-to-1. Also recall that every element in a function's domain must be sent to a unique element in its codomain. However, there's no requirement that every element of the codomain has a corresponding element domain. That is, there is no requirement that a function completely cover its codomain. If the function has the added property that every element in the codomain is covered, that is, every element of the codomain has an element from the domain that is sent to it, then we call the function onto, or surjective, or is a surjection. So formally, let f be a function from a set x to a set y. F is onto, or surjective, or is a surjection, if and only if given any element y and y, it is possible to find an element x and x with the property that y is equal to f of x. So here's an example of a function that is onto. Notice that every element in the codomain has an arrow going. Here is an example of a function that's not onto. Here we have 2 points, 2 elements in the codomain that do not have arrows going to it. Right, so the entire thing is not covered. So look at these 2 functions. We wish to determine which of these 2, if any, are onto. So we look here, b does not have an arrow going to it, so f is not onto. If we look over here, a, b, c, d, they all have at least 1 arrow going to it. So here we'd say g is onto. Right, now again, this is for functions on finite sets. Let's now look at functions on infinite sets. So we have 2 functions, f from the reals to the reals, g from the integers to the integers, and they are defined. F of x is 4x minus 1, g of n is 4n minus 1. I wish to determine whether either of these functions is onto, and again justify the answer. So we look at f, and we want to determine if it is onto. Well, this actually is onto. Right? All of the real numbers are covered by this function. All right, so the proof. Let y be a real number And we're going to define x to be y plus 1 over 4. Now maybe saying, hold up, how did you get x is y plus 1 over 4? Well, the answer is fairly simple. If this function is onto, then that would mean that y would have to equal 4x plus 1 for some x. At this point, you just solve for x. Right, so, I'm sorry, that should have been minus 1, not plus 1. So y plus 1 is equal to 4x, right? And so that would mean that x is y plus 1 over 4, and that is obviously a real number, right? It's a real number plus a number divided by a real number. So that's where this came from. Right, so we just have to show now that f of this is a real number. Or I'm sorry, is y, right? So this would be 4 times y plus 1 over 4 minus 1, right? The 4's will cancel out, so we are left with y plus 1 minus 1. 1 minus 1 is 0, and we are left with y. So therefore, f is onto. So now we look at g, and the idea is, can we get every integer from this? Well, what about 2? Can I get 2 out of this? No, right? No way I can multiply 4 by an integer, subtract 1, and get 2. So g is not onto. So we need to provide a counterexample. You could use the counterexample I just stated. However, let's say let y equal 0, and this is clearly a real number. Now let's suppose there is an n in the integers. I'm sorry, this should have been integer, not real number. There is an integer n such that g of n is equal to 0. Then this would mean that 4n minus 1 is 0. Add 1, we get 4n is equal to 1. Divide by 4, we get n is equal to 1/4. But this is not an integer, right? So we're saying that n is an integer and n is not an integer. That, my friends, is a contradiction. So there is no such n, so g is not onto. Now, a function can be one-to-one. A function could be onto. But a function could be both one-to-one and onto. And in fact, in the study of functions, and not just functions, right, but in the study of mathematics in general, functions that are one-to-one and onto are really important. So we give such functions a special name. We call such functions a one-to-one correspondence, or a bijection, or is bijective. Right, so again, a one correspondence is simply a function that is one-to-one and onto. So let's define a function big F from the reals cross the reals to the reals cross the reals as f of xy equals x plus y, comma x minus y. Is f a one-to-one correspondence? Now, for simplicity, I'm going to rewrite the Cartesian product of the real numbers with the real numbers as r squared. In fact, that is a very commonly used notation. Right, that is just the set of all ordered pairs such that the components are real numbers. Now, in fact, here f is a one-to-one correspondence. Right? It's one-to-one and it's onto. We just have to prove it. Right? So we have to do two things. We have to prove it's one-to-one. We have to prove it's onto. So for the formal proof, we're going to say let f be a function from r squared to r squared. Be a function defined as f of x, y equals x plus y, x minus y. So we must show that f is one-to-one and onto. So this is going to break down into two proofs. The first, that f is one-to-one. Second, that f is onto. So let's first prove f is one-to-one. So what we have to do is we have to take two elements of R2. So let's call them x1, y1 and x2, y2, such that f of x1, y1 is equal to f of x2, y2. Right, so the goal is we have to show that x1, y1 has to equal x2, y2. Right, so if these two functions are equal, then we must have x1 plus y1 comma x1 minus y1 is equal to x2 plus y2, x2 minus y2. Right, but this is true if and only if x1 plus y1 is equal to x2 plus y2 and x1 minus y1 is equal to x2 minus y2. Now, if we add these two equations together, we get 2x1, then we'd have y1 minus y1 is 0, equals 2x2. Well, this means that x1 has to equal x2. Now we just have to show that y1 and y2 are the same. We can plug it in. We can use a substitution in either equation, right? So I'm going to use it on the first equation. We're going to say, so x1 plus y1 equal to x2 plus y2 implies that x1 plus y1 is equal to x1 plus y2, which obviously implies then that y1 and y2 have to be the same. Therefore, x1, y1 has to equal x2, y2. Which means that f is indeed one-to-one. All right, so now we have to prove f is onto. Alright, so what that means we have to do is we have to show that for any ordered pair UV in R2, we can find an XY in R2 such that f of xy is equal to UV. And so we must show there is an ordered pair XY in R2 such that f of xy is equal to the ordered pair UV. Okay. So suppose f of xy does equal UV. Right, so we're going to do the other way of proving existential statements, which is we're going to provide a rule for finding this xy. Then x plus y, x minus y would have to equal UV. Right, but this is true if and only if x plus y is equal to u and x minus y is equal to v. Again, if we add these two together, we'll get that 2x is equal to u plus v, which means that x would be u plus v over 2. Now, if we plug this into one of the two equations, it does not matter which one. I will use, again, this first one. So x plus y equals u plus v over 2 plus y. That has to equal u. So this means that y is u minus u plus v over 2, which is 2u minus v all over 2, and that is u minus v over 2. So we have found that xy is equal to u plus over 2 comma u minus v over 2. Right, so therefore f of u plus v over 2, u minus v over 2 is equal to uv, which means f is onto. Therefore, our overall conclusion, f is a 1-to-1 correspondence. And the overall proof is complete. Right, so to prove that a function is a 1-to-1 correspondence, we must prove that it's 1-to-1 and onto. So we now look at a new type of function. So suppose that f from x to y is a 1-to-1 correspondence. Then there is a function f to the minus 1 from y to x that is defined as follows. Given any element y in y, f inverse of y is that unique element x in x such that f of x is equal to y. Right now, we're guaranteed that such an x exists because f is onto. We're guaranteed that it is unique because f is 1-to-1. We call this function the inverse function for f, or more simply, the inverse of f. So I already explained why this is true, right? So that the proof follows immediately from the definitions of 1-to-1 and onto, and so we will not look at an in-depth proof here. So here's an arrow diagram of inverse functions, right? So what happens is f will take an element x and send it over to y. What f inverse does is it takes that element of y and sends it back to x. So this function here, the function from the reals to the reals defined by f of x equals 4x minus 1, was already shown to be a one-to-one correspondence in the first two examples we did of this video. I'm sorry, not the first two examples, but the example of infinite one-to-one and infinite onto, right? We showed that 4x minus 1 was both one-to-one and onto. So it's guaranteed to have an inverse. We wish to find it. Okay, now, since f is onto, we know that for all y, all real numbers y, there exists a real number x such that y is equal to 4x minus 1. We also know that this x is unique because f is one-to-one. So what this is going to allow us to do then is to solve for this, right? Now, if you remember, when we actually did the proof of onto, I already did this, right? So here's how we do it, right? We set y, we set the function equal to y, and now we solve for x. So 4x would be y plus 1, which means that x is y plus 1 over 4. Now what we do is we replace the y's and the x's, so we switch their order, and we can write f inverse of x is equal to x plus 1 all over 4. And this would be the inverse of 4x minus 1. Now, if x and y are sets, and f from x to y is a one-to-one correspondence, then so is f inverse. So in other words, if f is a one-to-one correspondence, which it has to be to have an inverse, then the inverse is a one-to-one correspondence as well. So let f from x to y be a one-to-one correspondence. What we have to do is show that f inverse is one-to-one and onto. So first, the proof that f inverse is one-to-one. Let y1 and y2 be elements of y such that f inverse of y1 is equal to f inverse of y2. Then there must exist an x in x such that x is f inverse of y1 and x is f inverse of y2. Right? This is, by definition, the inverse. But this means that f of x is y1 and f of x is y2 by definition of the inverse. And so y1 is equal to y2, which means that f inverse is one-to-one. Now the proof that it's onto. Let x be any element of x. Suppose that y is equal to f of x. Then by definition, y would have to be an element of y. And thus by definition, f inverse of y would equal x. Well, so we just found the y. Hence, f inverse is onto, and that completes the proof. So now look at a third type of function. So let's consider two functions, f from x to y and g from y prime to z, such that y is a subset of y prime. This new function is called the composition of functions. So the composition of f and g is the function this here from x to z, which is defined as g of f of x. Now this is read g circle f, or I will probably be saying g composed with f, or simply read it g of f. This is read as g of f of x. So our diagram for composition, function composition, so f will take an element x, send it over to some element in y. Right now, g takes an element in y prime and sends it over to some element in z. Right now, since y is a subset of y prime, what f of g will do, what g of f will do is take that x and bypass this middle step, right? So essentially we're cutting out the middleman. I'm sure you've heard that saying before. It just takes x and sends it immediately over to that element in z. So let f and g be functions from the integers to the integers, defined as f of n is n plus 1, and g of n is n squared. We're asked to find both g of f and f of g, and decide whether f of g and g of f are equal. So first, for g of f, right, so this is g of f of n. Now, since f of n was n plus 1, this is g of n plus 1, right, but g was n squared, so this becomes n plus 1 squared. Now let's look at f of g. Right, so g of n is n squared, so this is f of n squared, which is n squared plus 1. Right now, n plus 1 squared is n squared plus 2n plus 1, which does not equal n squared plus 1 for any value of n other than 0. Now, in order for functions to be equal, they have to be the same for every possible value. So this means that if f is not equal to f of g. All right, so let x be the set 1, 2, 3, let y prime be the set a, b, c, d, let y be the set a, b, c, d, e, and let z be the set x, y, z. Define functions, f from x to y prime and g from y to z by the arrow diagram below. We want to draw the arrow diagram for g of f. All right, so the domain g of f is x, right? So 1, 2, and 3. The codomain of g of f would be z, which is x, y, and z. So we look at this diagram and go, okay, so f will send 1 to c, and then g sends c to z. So g of f would send 1 to z. So 2, f sends 2 to b, and then g will send b to y. So g of f will send 2 right to y. And then for 3, so f sends 3 to a, and then g will send a to y. So g of f will send also to y. And so there's our arrow diagram, for g of f. So now with composition functions, we actually have a new way to define inverse functions, right? So we could have used either the first theorem or this one to define an inverse function. So if f from x to y is a one-to-one correspondence with inverse f inverse from y to x, then f inverse of f is equal to I sub x, and f of f inverse is equal to I sub y, where I sub x, where I sub x goes from x to x and is called the identity function on x, which is defined as I sub x of x is just x, right? So whatever element I'm actually pulled into it, it spits that value right back out. So let f from x to y be a one-to-one correspondence with inverse f inverse from y to x. So there are two things we have to prove, right? We have to prove that f inverse of f is I sub x, so just x. And then we have to prove that f of f inverse is I sub y, or just y. So let's do the first proof. So let x be any element of x. Then by definition, f inverse of x is f inverse of f of x. So define z to be f inverse of f of x. Then we would have that f of z is equal to f of x. However, f is 1 to 1. So we must have that z is equal to x. But z was f inverse of f of x. So that means that f inverse of f of x is equal to x. Well, since we plugged in x, that means that this has to be the identity function on x. So for the other proof, that will be left as an exercise. But it is very similar to this proof here. And that would complete the proof. So if f goes from x to y and g going from y to z are both one-to-one functions, then g of f is also one-to-one. So the composition of one-to-one functions is one-to-one. So let's suppose that f from x to y and g from y to z are both one-to-one functions. Then this means for every x1 and x2 in x, and for every y1 and y2 in y, f of x1 equaling f of x2 means that x1 is equal to x2, and g of y1 equaling g of y2 means that y1 is equal to y2. Suppose that x1 and x2 are elements of x such that g of f of x1 is equal to g of f of x2. Right, so by definition, g of f of x1 is equal to g of f of x2. Right, what we have to do is show that x1 is equal to x2. So define y1 to be f of x1 and y2 to be f of x2. Then this would mean that g of y1 is equal to g of y2, right, by substitution. Right, however, this would mean that y1 and y2 are in y, and by definition of f, we must have y1 is equal to y2, because f is 1 to 1. Oh, I'm sorry, since g is 1 to 1. So, f of x1 is equal to f of x2, which means x1 has to be x2, because f is also 1 to 1. Oh, so we just showed that x1 and x2 are the same. This means that g of f is 1 to 1, and so our proof is complete. If f from x to y and g from y to z are both onto functions, then g of f is also onto. So what this says is the composition of onto functions is also onto. So suppose that f goes from x to y, g goes from y to z are both onto functions. then what this means is for all y and y, and for all z and z, there exists an x in x, and there exists a y prime in y, such that y is f of x, and z is g of y prime. Now let z be any element of z. We must show that there is x in x, such that z is equal to g of f of x. Now, since z is in z, there must be a y in y, such that z is equal to g of y, right? Because g is onto. However, y is in y, so this means there has to be an x in x, such that y is equal to f of x. So combining these two statements, we have there exists an x in x, such that z equals g of f of x, right, by substitution. This is what to be shown, so g of f is onto, and the proof is complete. And now, as a direct consequence of these two theorems that we just proved, if f from x to y and g from y to x are both one-to-one correspondences, then g of f is a one-to-one correspondence. So the composition of one-to-one correspondences is also a one-to-one correspondence. This concludes our look at functions. This also finishes relations and functions. So in the next video, we will begin looking at counting.